Hi everybody, this is a video for my Intro to Calculus students, and we're going to be doing the second part of the implicit differentiation lesson. This one's a little bit longer than the last one, and we're going to do 6 examples where we don't have to explicitly define y in order to find the derivative of an equation. So we'll start here by thinking back to the first example from the last lesson. It was a circle, and it was x squared plus y squared equals 225, which we have graphed here. And we pointed out in the last lesson that this is definitely a relation, but it's not a function, right? It fails the vertical line test. And we solved this problem by rearranging this so that we had y equals plus or minus 225, the square root, of 225 minus x squared. And then we treated that as 2 separate equations, a positive one and a negative one. And with the new method we're going to learn today, we actually don't have to do that. We can, to solve the problem, find the slope of the equation where x is 9. We can solve this without isolating this equation for the y value. And when you leave the equation in this form, you would say that it is x is implicitly defined by y. It is not explicit because it's not y equals. So this is an implicit relationship, and what we're going to do now to define the derivative of it is called implicit differentiation. So this is method 2. Method 1 was what we did in the last video, and we'll just start by, again, rewriting the equation. X squared plus y squared equals 225. And remember, what does it mean to find the derivative? Well, if we want to find the derivative, remember that the derivative, dy by dx, is also, of course, the rise over the run, right? It's basically delta y over delta x, right? It's the slope. So I want the slope when x is 9. And notice there should be 2 answers for that, right? There should be a tangent here and a tangent here when x is 9. I didn't draw that one very good, but you get the idea, right? So I would like to know the slopes here and here, and I'm going to do that by something called implicit differentiation, which is really just an application of my chain rule. Okay, well, you know what? Maybe the first thing I'll actually do is I'll find out the coordinates of this point. I know that this is 9 comma something and 9 comma something. So let's find that first. So if I put in 9 squared plus y squared equals 225, I'm going to get 9 squared is 81. So y squared is going to be 225 minus 81. So y is going to equal plus or minus 12 because that's 144 square rooted. So that means that this would be the negative 12 and this would be the positive 12. So let's see what I can do. So I want dy by dx. So dy by dx is what I'm looking for. And let's find it algebraically. So I want the derivative with respect to x for x squared plus y squared equals 225. So I want the derivative with respect to x to all of these 3 terms. Well, the first one's pretty easy, right? That's just 2x. But what about this one? Well, remember how when we did chain rule and we found the derivative where we had, say, a u here and then u was another function defined in terms of x? Well, what we do is we would take, okay, the exponent becomes the coefficient, and then you'd go 2 minus 1 for the exponent on that, times the derivative of the actual of y, but that I'm going to have to leave as the derivative of y with respect to x, right? I need the derivative of what this function is, and I don't know what this function is defined as x, so I'm going to have to leave that kind of as a variable. Of course, the other side of the equation, the derivative of a constant is always 0, and of course the exponent becomes 1 here. And then this, remember, is actually what I want to solve for. So this thing that I usually use in my Leibniz notation as a function, as something it's telling me what to do, like sine or square root, Now I'm actually going to treat it like it's a variable, and I'm going to solve the equation for it because that's going to be my solution. So dy by dx is going to equal, all right, so I'd move 2x to the other side and it'd become negative 2x. And this would still be times here, so I'll just do this in 2 steps. So I'm going to divide both sides of the equation by 2y. All right, the 2's will cancel, and I'll be left with negative x over y. And this was what I wanted to solve for, so that's actually my answer. That's the equation of the slope all the way around this circle. And I wanted to find the slope when x was 9. And when x is 9, remember that y can be either positive or negative 12, so I have 2 solutions. Therefore, my slope would equal, well, if I use positive 12, my slope dy by dx would equal negative 9 over 12, which is negative 3/4. Or my slope would equal negative 9 over the other value, negative 12. And my slope would be positive 3/4. And that, oops, I meant to underline that. That tracks for the diagram, right? Obviously one of these, the one with the negative y exponent, or y coordinate I mean, has a positive slope, and the one with a positive y coordinate has a negative slope. And just to, you can check to see if you've done these right on Desmos, which we've been kind of showing you for the most of the course that you're doing this kind of stuff. You can check to see if you've done it right. Here's the circle. Just got to zoom out a little to see it. There it is. So there's the circle. Here's the point that I found, 9, 12. Here's the other point that I found. And I can zoom around and find points. But what I can't do, we've actually kind of reached the limits of what Desmos can do for us. Desmos actually won't do method 2 and allow me to just do straight up implicit differentiation on this. You would have to actually change it to y equals and then do dy by dx, which is basically method 1. But I can still check to see if my answer is right, because if my answer is right, then with the slope of negative 3/4 and x is 9 and y is 12, I should have, at this point here, a tangent line. And I do. And then what happens when I plug in 9 and positive 12? Well, I should get, with a positive slope of 3/4, another tangent line, and I do. Now, as these get more complicated, you might not be able to tell exactly just visually if you have a perfect tangent line, but you'd be at least close enough that you could find any minor errors in your calculation just visually. So there's the first one. That'll be our example 1. Example 2 says, determine the slope of the tangent to the curve x cubed plus y cubed equals 9 at the point 2, 1. Let's see if I can make that less blurry. That's worse. Come on, you. Oh, come on. 3rd time's the charm. Let's go. Oh, dear. One more time. Come on. I don't know why it's doing this. Let's see if I move it. Maybe that'll help. Maybe if I give it a little something in the foreground. Okay, one more time. Come on, you thing. There we go. And now let's get a little closer. Slowly. Sorry about that, folks. I don't know what's wrong with this thing right now. There we go. Okay, so sorry about that. All right, example 2 is I would like to find the tangent to the curve and at the point 2, 1. So again, I'm going to do the first thing here is I'm going to actually, in Leibniz notation, find the derivative of this entire equation. And that means that I want the derivative with respect to x of x cubed, which is easy. That's 3x squared. Now, this is chain rule, right? So I want the derivative with respect to x of something that isn't x, which means I got to use my chain rule. So it's going to be 3y squared times the derivative of what's inside the y function, which I don't know what it is. So I'm going to have to call that dy by dx. Okay, and of course, derivative of 9 is nothing. So I'm going to solve for dy dx because that is my slope. So dy by dx would be, let's see, we'll move the 3x squared to the other side. And then we'll divide, that would actually leave it like this. Maybe I'll do it in 2 steps again. And then I'll divide both sides by 3y squared. It'll cancel my 3's and leave me with negative x squared over y squared. Notice you can't cancel those squareds. Please don't do that. And of course, we were using the point 2, 1. So dy by dx would equal the negative of 2 squared over 1 squared, which would equal negative 4. Okay, and once again, let's see if hopefully this doesn't mess up our focus again, but I'm going back to my picture. This is an interesting little curve. It's kind of a, like a speed bump sideways. And, okay, we wanted the point 2, 1, which is on the curve. And we think that the slope is negative 4 when x is negative 2, or when x is 2 and y is 1. So that should make a tangent line, and looks pretty good. Looks like it does. Okay, so that one's checked. Oh, good. We're still in focus. That's good news. All right, example 3. We've already done a circle. Let's do the circle's close friend, the ellipse. Find the slopes of tangents to the ellipse 2x squared plus y squared equals 36 when x is equal to negative 4. So what's that going to look like? Okay, well, once again, I'm going to start by going d by dx of 2x squared plus y squared equals 36. And I'm actually going to use a slightly different notation this time. You always start in this Leibniz notation, but some people don't like using dy dx as a variable. So it's perfectly legit to, okay, well, the derivative of 2x squared is 4x. And then the derivative of this thing is going to be, well, let's see, it's 2 times the thing inside the exponent, which is y, to the power of 1, because you minus 1 from the 2, times the derivative of y itself. And I can call that y primed. Now, I don't actually usually like doing it this way. I just decided to do it this way because if you see it in another textbook or something, you should be ready for it. Of course, once again, the derivative of 36 is nothing. The reason I don't like it is because sometimes I'm very bad at forgetting primes, but I never forget a d dx or a dy dx. So this is still the same exact statement in terms of saying this is y primed instead of this is dy dx. Good enough. So once again, I need to solve for this. This is what I'm looking for. It is my slope. So I'm going to say 2y times y primed is equal to negative 4x. And y primed is equal to negative 4x over 2y. The 2 cancels into the 4, leaving me negative 2x over y. And okay, I have to figure out when x is negative 4 how much y squared is. So that's going to be 2 times negative 4 squared plus y squared equals 36. 2/16 is 32. When you minus 32 from 36, you get 4. So y is equal to, again, plus or minus 2, which makes sense. Right, when x is negative 4, looks like there's a spot here at 2. So negative 4, 2. And there's a spot here at negative 4, negative 2. And we're going to have, again, a tangent this way and a tangent that way. And I need to find the slopes of those tangents, and they are, the equation for the tangent everywhere around here is negative 2x over y. But I am going to plug in the 2 points, and they are, so I'll say therefore dy by dx is equal to negative 2 times, okay, so when x is negative 4, y can be 2, in which case the slope would be 8 over 2, which is 4, or the y value could have been negative 2, so I'd have negative 2 over negative 4 all over negative 2, in which case I'd get negative 4. And once again, I'll check that with my Desmos to make sure I did it right. So, okay, that's the next one down here. Here's the ellipse. Here's one point that I'm looking for the slope at. Here's the other point that I'm looking for the slope at. And then, of course, if I have this right, then the slope of 4 should be one of the tangents, and the slope of negative 4 should be my other tangent. And they are. Looks pretty good. Okay. Let's move on to example 4. Okay, no blurries, no blurries, no blurries. Yay. Okay. All right, example 4. Find the derivative if I have the equation x cubed plus x squared y plus 4y cubed equals 6. There's now kind of a difference between example 3 and example 4. For one thing, and example 1 and 2. The first 3 examples we did today, we could have done by the method in the previous video that Mr. Lacko showed you. We could have very easily written this thing as 2 equations in terms of y, a positive one and a negative one, just like we did in the last lesson. Good luck trying to isolate y in this equation. How would you do it? You could factor y out of here, but then you'd still have a y squared there. It would be kind of nasty algebraically to try to figure out a way to solve this thing and isolate y. So that's where we're kind of stuck with method 2. We have to learn how to use this implicit differentiation and chain rule. This couldn't easily be made explicit. So I'm going to find d by dx of my equation. Oops. Oh well. I'll just say, get rid of that. Sorry, didn't mean to put that there. This is the problem with writing in pen. And let's see. That's going to be 3x squared plus, okay, now I have to use product rule, right? So what would product rule be? Well, product rule would be the derivative of x squared, which is 2x times y, plus x squared times the derivative of y. But the derivative of y, of course, I don't know, so I'm going to call that dy dx. Everybody get how this became that using product rule? And of course, the derivative of 4y cubed, I have to use chain rule on. That's going to be 4 times 3, which is 12. Then the exponent becomes 1 less. But then I have to times it by the derivative of y, which is, of course, dy by dx. Okay. Now, what am I going to do with that? Oh, yeah. Equals 0. What am I going to do with that? Well, I have to solve this thing for dy dx. So everything that isn't dy dx is going to move to the other side of the equation. So I'm going to leave x squared times dy dx plus 12y squared times dy dx on this side. And on the other side, I'm going to have negative 3x squared minus 2xy, right? Because I moved those two things to the other side by subtracting them. So now I'm going to factor the thing I'm solving for, dy dx. And that gives me that. And then I'm going to divide both sides of the equation by this bracket. It'll cancel on the left. And this rather cumbersome looking expression here is my slope. And that's the best I can do with it. Now, this one gets very, very difficult to check with Desmos. I did punch it in just for fun here. There we go. There it is. It's another one of these graphs that's kind of like a sideways speed bump. And luckily, there is an actual point here. 1, 1 is on there. If you look at the equation, you can see that 1, 1 works very easily. 1 plus 1 plus 4 is 6. So 1, 1 is a point on here. I could actually add it. Let's see. I'll add it as point V. 1, comma 1. There we go. And then I could run 1, 1 through this expression that I have here. In fact, if I did that, I'll say I'll check with the point 1, 1. And let's see, if x and y are both 1, that's going to be, my slope would become -5 over, is it 13? Yeah, -5 over 13. And so I can check with that. I don't have this one typed in, so I'll just type it in really quick here. I'll just say y minus 1 equals 5 over 13 times x minus 1. And, oh, hang on. I forgot the negative. There we go. And there we go. That looks pretty good. Looks like it's a tangent. Now, I kind of got lucky that this thing goes through 1, 1. There is actually no guarantee that a complicated curve will ever have nice integer points. In fact, Fermat's last theorem even tells us that, let me just go to a piece of scrap paper real quick here and explain what I'm talking about. Fermat's last theorem tells us that we know that there's actually infinite solutions for ax squared plus bx, or plus a squared plus b squared equals c squared, I meant to say, because that's Pythagorean, right? There's infinite. 3, 4, 5 works. There's infinite answers. But Fermat's last theorem proved that this has no whole number solutions that aren't trivial. Like, for example, if a or b was 0, there's a solution. But other than that, assuming you have something where it doesn't go through a 0, curves don't have to have integer solutions. In fact, finding integer solutions for complicated curves is like an entire branch of number theory called Diophantian equations. So you can't always easily check these using Desmos. Sometimes you just have to kind of double and triple check your algebra and make sure that you have the right solution. This one I managed to find a point fairly easily. I don't know if I can for example 5 or not. We're going to do just a couple more here. Let's see, what did I have for example 5? Find the derivative of that is what I've got for example 5. Okay, so let's do that. Feel free, by the way, if you're finding this easy, to pause the video and try it for yourself. I'm going to just go right into it here. I'm going to find the derivative with respect to x of x minus y squared. And I'll just do this as sort of two sides, the derivative with respect to x of x plus y minus 1. So, let's see. Chain rule that, which means that this exponent becomes a coefficient. And then you leave what's in the bracket alone. And then you have to find the derivative of what's inside the bracket. Remember, this 2 became a 1. I'm not going to bother writing a 1 for an exponent. But now I have to find the derivative of what's inside the bracket, which would be 1 minus the derivative of y, which is dy by dx. The other side of the equation, the derivative of this bracket, is 1 plus dy dx. And the derivative of 1 is 0. Now what? Well, I kind of have no choice but to actually multiply that out. So I'll start by distributing the 2. Remember, my goal here is to eventually simplify this equation for the derivative, right? The derivative is dy by dx. That's what I'm looking for. That's what I have to solve here. So I'm going to have to first expand this so that I can isolate these two guys together and collect them as like terms. So, foiling that out, I'm going to get 2x times the two things in the brackets. Then I'm going to get minus 2y times the two things in the brackets. And I can't add these two things together, and I can't add those two things together. They're not like terms. dy by dx is like a new variable. It's like a z. So these two things, or sorry, these two things and those two things aren't like terms. Make sure we understand that. Okay? But these three things are like terms. So I'm going to move them all to one side of the equation. So I'm going to leave the minus 2x1. This one is going to stay over here. And this one's going to stay over here, 2y times dy dx. And I'll subtract this one from both sides of the equation. So it's over here. Then I'll get this 2x and this 2y to the other side of the equation, so that'd be 1 minus 2x, and this is a negative 2y, so I'll add it on this side. Take a second and make sure you understand the algebra that I just did to get all the derivative terms on one side of the equation. Then factor it out, and I'm going to have negative 2x plus 2y minus 1 equals 1 minus 2x plus 2y. And then for my very last step, I'll divide both sides by this bracket. And that is going to be my answer. And that's that one there. Again, I put it on Desmos. I kind of wanted to see what kind of a curve this this weird thing was when I started. And here's what I got. Okay, I can get rid of this guy, get rid of that guy. So I got this, get rid of that one. Here's the curve that I got. Notice this one doesn't have any easy to find points. So I didn't really have a way to check this one, right? Again, it is completely conceivable that this thing could get infinitely big and actually never have integer solutions for x and y. It is completely possible. It probably does, but I can't see them, and certainly there's no zeros to help me. So I just kind of said, nope. I've run out of a place where Desmos can help me. Interestingly enough, too, if you drag along here, sometimes you can get lucky and find coordinates that match, but I tried that for a while and it didn't work. And even more interestingly, if you go to something where x or y is cubed, Desmos can't even calculate. Notice it won't let me run along and find points. I've kind of reached the maximum of what Desmos can do. It doesn't have the power to calculate points as you drag along when the equation gets this complicated. So again, using Desmos to check these answers sometimes isn't going to work out. So we're just going to have to check the answer key for that one. I did double check it. I'm pretty sure I did example 5 right. Let me know. Email me if you notice I've goofed it up. We'll do one more and call it a day. Find the slope of that when x is 1. So once again, we're back to kind of doing a solution here. And all right, so let's see. Ran this one through. So I want the slope at x equals 1. So I'm going to go d by dx of x squared plus y minus x cubed equals, and dy by dx of 28 is just 0. So I'll just put the 0 on that. All right, so I'm going to find the derivative of x squared. That's 2x plus. Now I need my chain rule. So that's going to be 3 times y minus x squared times the derivative of what's in the bracket, which is going to be dy by dx, right, the derivative of y, minus the derivative of x, which is minus 1, and all of that equals 0. So let's move the 2x to the other side. Okay, and let's divide both sides of the equation by that. So that's going to be negative 2x all over 3 times y minus x squared. And then to isolate this, all I got to do is add 1 to both sides. Okay, and in the old textbook I stole this example from, when I first did this, this wasn't the answer the textbook had. They tend to usually in the textbook want this all to be one thing. They consider it more simple if you can make this one rational expression. So to do that, you would find a common denominator, and the common denominator would be 3 times this. So I'm going to times 1 by 3 times y minus x squared. So I'm going to get negative 2x plus 3 times y minus x all squared all over 3 times y minus x all squared. Now, having said that, that's the final answer for the derivative. But I actually really, what I wanted was to find out the slope when x is 1. So actually, this one here is kind of easier to work with than this one. So this is a better final answer if I need the derivative. That's what the textbook will say. But if I'm actually going to have to work with it and plug in x's, I think that's easier. Now, if I'm going to plug in x, I also have to plug in y. So I think the first thing to do is to go, okay, so when x is 1, how much is y? And 28 minus 1 is 27. Now, I'm glad this came up. When I square root both sides of the equation, I have to consider plus or minus. Do I have to do that if I cube root both sides of the equation? And the answer is no, because remember, if you cube a negative, you get a negative. So you don't have that ambiguity if you're cube rooting. So this will be just y minus x is the cube root of 27, which is 3. Oh yeah, and x, what am I doing with an x here? X is 1. Duh, sorry. I plugged in a 1 here and I forgot to plug it in there. And but that's okay, you can plug it in whenever you want. I'm ready for it now. So it looks to me like I have y minus 1 is equal to 3. So y is equal to 4. Okay? And then since dy by dx is this thing, I'm going to plug that in. So dy by dx is equal to negative 2. And again, my x value is what they gave me, right, is 1. So I'm actually at the point 1 comma 4. So that's negative 2 times 1 all over 3 times y is 4. 4 minus 1 all squared plus 1. And that's going to be negative 2 over 3 times 9. So that's negative 2 over 27 plus 1. Do a quick arithmetic on that, and I'm going to get 25/27. So let's see. If I start with this curve and the point 1, 4 with that slope, do I get a tangent line? Let's see. Oops. Let's see again. There we go. All right, let's make that curve go away. So there's the curve I just played with. That one's really interesting. Check that one out. There we go. And there's the point 1, 4 that I found. And here's the equation. Does it work? And it looks like it does. So that is how you'd solve problems like this. Now it's time for you to try some and play with the homework. And please join us on the live chats or message me in team if there's anything you have any trouble with. Thanks for watching.